okay?
It's okay. Please use that mic.
Yeah. Okay. Right, good morning. So, this is the final talk for me for this GIAN course. I really hope that you had a good time. So, this one is mostly applications, how we can use multiferroic composites for devices operating at very high frequencies. So, the unique thing about multiferroic devices that you can tune it with either an electric field or a magnetic field. So, tuning with the voltage makes possible to miniaturize all the devices that I am going to talk about. So, we all know what we have been discussing for the past 4 days is that there is strain mediated coupling between the ferromagnetic and ferroelectric phases in a composite. So, if you have a bulk composite, then the strain is rather internal within the sample. And for the case of a layered structure, then it is interface strain. So, if you apply an electric field, there is piezoelectric strain, which would alter the properties of the magnetic field. This is the one we will be using for most of the applications for tunable ferrite devices. There is another option where we have a layered structure of a ferroelectric and a ferrite, and you can excite 2 types of resonances. One is ferromagnetic resonance in the ferrite and dielectric resonance in the ferroelectric. When they combine together in the frequency spectrum, you have what are called hybrid waves that can be tuned with either an electric field or a magnetic field. So, the advantage is the hybrid waves can be tuned over a wide frequency range compared to pure ferromagnetic resonance. So, we will discuss devices based on both ferromagnetic resonance as well as hybrid waves. Right. So, you are familiar with how we can study the nature of the converse magnetoelectric effect at ferromagnetic resonance, and also I will talk about how the hybrid magnetic dielectric modes behave under an electric field. Then for the device applications, I will discuss resonators, filters, phase shifters, delay line and attenuators. Miniature antennas we already discussed yesterday, so I won't be repeating that again. Right, you are familiar with this picture where we show a bilayer of a ferrite and a ferromagnet on the ferroelectric, and then you excite ferromagnetic resonance in the ferrite, then you apply an electric field, there is a shift in the resonance field. So, you estimate the shift in the resonance field as a function of the electric field. Then you draw a graph relating delta H to E, and the slope of that would be the coefficient of the converse magnetoelectric coupling, this term A. Now, we are going to discuss most of the devices based on yttrium and garnet. It's not highly magnetostrictive, but the advantage is it has very small line width and very low high frequency losses. So, it is a preferred material for most of the applications for devices operating up to 12 gigahertz. So, when you go higher in frequency, the problem is like for any YIG device, you have to have a biased magnetic field to operate. The higher the frequency, higher the field that you need. So, for 10 gigahertz, you need a field of 3 kilohertz. So, if it is 15 gigahertz, it is much higher, 5 or 6 kilohertz. So, the power requirement keeps going up and up as you go up in frequency. So, instead of using YIG at frequencies more than 12 gigahertz, what we prefer is either nickel ferrite or lithium ferrite. They are good up to 20 gigahertz. Then one can use hexagonal ferrite for 20 to 50, Y type or Z type and so on. For frequencies above 50 gigahertz, one has to use hexagonal ferrite with M type structure, either barium or strontium ferrite, and they are good up to 110 gigahertz. Okay. And for the composite, we are going to use either PCT or PMNPT. They have reasonably good piezoelectric constants. So, we did some theory, and the magnetoelectric coupling coefficient for converse magnetoelectric effect is given by the second term here. So, it is directly proportional to the product of the magnetostriction and the piezoelectric coefficient, and it is inversely proportional to the magnetization for the ferrite. So, these are some of the values of the important parameters for the ferrimagnetic oxides, and you are looking at yttrium and garnet. It can be you can have films with line width as small as 0.5 Ørsted. So, that is a key parameter, because when you tune a device, the question is what is the tuning range compared to the line width. So, if I can tune the device by several line widths, that is what we prefer. So, that is where the advantage of using YIG comes in. Nickel ferrite and lithium ferrite, they are not, they have a slightly higher line width compared to yttrium and garnet. So, lithium ferrite has about less than 10 Ørsted. It is rather difficult to get 2 Ørsted, that is the value mentioned here, but it is a challenge. And nickel ferrite has a much higher line width, even in the form of a single crystal film between 25 and 50. Nickel zinc ferrite also large line width, and Y type zinc 2Y, it has a reasonably good line width, but these are all single crystal films. If it is polycrystalline, they are no good for device applications. The line width is too high, and it is not going to work. So, these are the magnetostriction around 100, 110 and 111, and looking at these numbers, the best values are for nickel ferrite. Lithium ferrite is also okay. The worst is yttrium and garnet. So, this one I showed in one of the earlier talks. It shows the FMR profiles, which is actually the derivative of the power absorbed by the samples under two conditions: no electric field, that is E equal to 0, then an electric field of 300 kilovolts per centimeter. And in each case, yttrium and garnet PCT, nickel ferrite PCT, and lithium ferrite PCT, there is a downward shift in the resonance profile. Then, if you estimate from these profiles, these are theoretical simulation, and then you get these numbers here at the bottom for the shift in the resonance field. It is the smallest is for YIG PCT, that is 20 Ørsted. So, you can find the converse magnetoelectric coefficient for each and every case. For EG, it is 20 divided by 300, it's rather small. For nickel ferrite, it's about 1 Oersted centimeter per kilovolt, and it's little bit smaller for lithium ferrite, which is 75 over 300, that's 0.25 Oersted centimeter per kilovolt. So, in all these three cases, you can use the device at ferromagnetic resonance and then tune them with an electric field, if that's what you want to do. But the tuning is rather limited. And also you have to keep in mind that in each device you must have a biased magnetic field. So, the tuning in this case is small, but it is good enough if there is a device operating at room temperature and you want to make it operate over a wide changing in the temperature, maybe from 0 to 60 degrees, then the tuning that you can do with the voltage is enough to compensate for any shift in the temperature of the device. So, it is rather very limited capability, and we cannot tune the device over several operating bands. That is not going to be possible. Okay. So, as I mentioned earlier, depending on the frequency where you want to operate the device, you have to choose the appropriate ferromagnetic oxide, and 1 to 10, maybe 12 gigahertz, yttrium and garnet. These are usually deposited on gadolinium gallium garnet substrates, and the best technique for depositing these films on GGE would be liquid phase epitaxy. For single crystal Z and Y type ferrites, you can use LPE, but you may have to use other techniques such as pulsed laser deposition or chemical vapor deposition. And then barium and strontium ferrite, and also aluminum substituted barium and strontium ferrite. These single crystals, they are bulk single crystals. They are made by floating zone technique. I discussed this some time ago, where you have two halogen lamps, you heat a polycrystalline seed to about 1700 degrees Celsius, then there is a small sample of single crystal seed. So, once you start cooling the polycrystalline seed at very slow state, like 1 degree per minute, the cooling should be very slow for it to grow the single crystal. It is in the form of a cylinder, and then you can put together this kind of system to make a long rod of single crystal M type ferrite. Then it has to be annealed at very high temperature in oxygen atmosphere, because during the growth process you always tend to have iron 2+ in the ferrite, which you do not want, because if there are divalent iron in the crystal, that would make the sample more conductive electrically, and that will lead to losses when you use them in the device. So, the growth followed by annealing in oxygen at high temperature and high pressure of oxygen, it is a key ingredient when you make single crystal M type ferrites. And then we can form bilayers with PMNPT or PCT, and it has to be done by some kind of a bonding technique. It can be epoxy bonding, eutectic bonding, or silica bonding. In silica bonding, you can sputter a thin layer of glass, then heat it up at high temperature and apply some pressure. between the ferroelectric and the ferrite, and that will lead to good bonding. But we tried all three of them. The best one and the easiest one is just the epoxy bonding. It works very well, and you don't need any fancy technique, but it's okay so long as you don't have any heating associated with the device. If the device heats up, then there is a danger of debonding the ferrite and the ferroelectric, and the device won't work anymore. So, this is the experiment where you look at the shift in the ferromagnetic resonance in an electric field and estimate the converse magnetoelectric coefficient. And this is one example that I showed earlier. It's on yttrium and garnet, and these are the first derivative of the power absorbed by the film. And as you apply an electric field and increase its magnitude, there is a shift in the resonance to the right. And here this graph shows the plot of shift in the resonance versus electric field, and the slope is the converse magnetoelectric coefficient that comes out to 5 Ørsted centimeter per kilovolt. Okay, so this is the hybrid waves that I am talking about earlier. What we have here is a ferroelectric layer made of barium strontium titanate, that is BST, and BST has very high dielectric constant, and when you apply an electric field, you can tune the dielectric constant pretty well. So, that is a key ingredient in these hybrid wave devices, because the tuning involves varying the dielectric constant, and that is the reason we are using not barium titanate, but barium strontium titanate, and there is an yttrium and garnet film on a GGG substrate. They are bonded together, and the tuning voltage is applied across BST. These are the dimensions for the egg film and the BST platelet. So, what you see here is a magnetic mode in combination with dielectric resonance in BST, which is the hybrid mode that is represented by 1. So, as you increase the voltage across BST, the dielectric constant in BST changes. That leads to a large tuning capability for the hybrid mode, and you can tune it by about 25 megahertz for a voltage of around 1000 volts. That is very high, but that is what we did. And the Q value for the resonance is rather high, it is about 1000. So, but this tunability is much better than the previous one here, where you can tune it by 40 Ørsted in an electric field of 8 kilovolt per centimeter. In frequency term, it is only about 100 megahertz. In this case, the tuning is 25 megahertz for a voltage of about 1000 volts. It is about comparable, but you can do a lot more with the hybrid waves, as I am going to discuss later. So, this is the electromagnetic frequency spectrum, and the range where the devices would operate is rather limited. 1 gigahertz is 10 power 9. So, we are talking about devices from 1 to 100 gigahertz, that is 10 power 9 to 10 power 11, and that is where it is a small region here, but that is where these devices are useful. Okay. So, the key parameters for the materials that are going to be used in the devices are high resistivity to reduce any losses, and also you need high magnetization and high Curie temperature, In case of heating, you don't want to have the device perform very poorly. So that requires a much higher Curie temperature for the magnetic oxide films compared to its operating temperature. And you also preferably use films with low ferromagnetic resonance line width. So the devices that you would like to put together, depending on the frequency, these are the choices for the magnetic film. Yttrium and garnet, then up to 10 gigahertz. Spinel ferrites, both lithium and nickel ferrite, up to 15 gigahertz. Then the hexagonal ferrite, Y and Z type, the maximum limit is 30. And for M type, it's between 30 and 110. So these devices are used in phased radars, and they include resonators, filters, phase shifters, and so on. They are front-end elements in phased radars. And as I mentioned earlier, if you want to tune the operating frequency, then you generally use a variable magnetic field produced by a solenoid or an electromagnet that would make the device power hungry and also too big for any miniaturization. And also it can integrate them with any semiconductor devices. Okay. And also you have to deal with very large size and weight. So this is called swap: size, weight, and power. So the whole idea is to reduce the swap needed for these devices, and one of them is shown here, and it's a hybrid wave device with BST and YIG, and it's placed on this strip line. It can be used as a resonator or a filter, but it can be it's bonded to PZT and put it on this microstrip line, and then you excite it with microwave power. At ferromagnetic resonance, it will absorb the microwave power. So if you have an output arm, then this is a band stop filter where it will absorb power over a certain frequency range. So it can be used as a filter, but we'll get to it pretty soon. Okay. So before we came up with all these composites, people did some experiments and how to tune the YIG-based devices without varying the magnetic field. So these were published work in the late 1980s and early 90s, and this is a work from Ukraine where they used an YIG film on GGG, and they looked at the ferromagnetic resonance in the YIG film. Then they applied a mechanical force onto the film, and depending on whether the force is either tensile or compressive, they are able to tune the ferromagnetic resonance, and that's what is shown here. So in one sense, there was increase in the resonance field, and when it was compressive, the resonance field decreased. So they were able to demonstrate that you can tune it with a mechanical force. Why does it happen? If when you apply a force to it, it's like the magnetostriction, right? It would change the magnetic properties of the film. It can change either the magnetization or the anisotropy field. That would manifest as a change in the resonance frequency. So that's how they were able to demonstrate the tunability with a mechanical force. So we are doing essentially the same thing, except that the force is created by the piezoelectric strain in the composite. Okay? So I'll talk about these devices: resonators, band pass filter, phase shifter, attenuators, and delay lines. and based on hybrid waves, resonators and phase shifters. Right. This is the ferromagnetic resonance in a polycrystalline multilayer of lithium ferrite and PZT, and look at this FMR profile. It has the line width. The line width is the separation between this dip and the peak. That's close to 800 Ørsted, and even you apply very large electric field as shown here, the tuning is by a very small static magnetic field, right? It's practically nothing, it's just 80 Ørsted. The line width is 800, it's a tenth of the line width, so the tuning doesn't serve any purpose, right? So, the polycrystalline material is not something you want to use in any of the devices. It should be single crystal ferrites with reasonably small line width, so that the tuning is by several line widths. So, one of them is shown here. This is a resonator, and in this device the PZT platelet is bonded to EEC film on GGG substrate, and this is a strip line on an alumina ground plane. You place the film along with the PCT right onto the strip line, and you can apply a bias magnetic field either parallel to the plane or perpendicular to it. Then you excite with microwave power, and there is a vector network analyzer which is a source of microwave power, as well as it can measure the power reflected from the film or the transmitted power. So, what is shown here in the bottom profiles are the reflected power in this case as a function of frequency. So, the ferromagnetic resonance would show up as a sharp dip in the reflected power. That is because under ferromagnetic resonance, the sample, in this case EEC film, would absorb power. So, there is a dip in the profile. Then you apply a voltage across PCT, depending on the polarity of the electric field. There is a shift in the FMR profile to either higher or lower frequency. Then you plot the shift as a function of the applied electric field. So, in this case, the PZT platelet is 0.5 millimeter thick. So, to create a field of about 10 kilovolt per centimeter, you have to use about 500 volts. Okay, that's pretty high, but it can be. There may be difficulty applying that kind of a voltage in a practical device. So, the only option is to decrease the thickness of PCT. You do not have to use 0.5 millimeter thick PCT. Instead, you can decrease it to 0.1 millimeter, which is about 100 micron, and that would give you the same kind of electric field for 50 volts rather than 500 volts. Okay? And these data in the shift in the FMR are shown for two cases. One is the static magnetic field parallel to the plane, and the other is perpendicular to it. And when you change the polarity of the electric field, the strain switches from compressive to tensile, and so there is a downshift in one case, an upshift in the other case, and overall the shift in the ferromagnetic resonance is around 60 megahertz for electric field span of plus 10 to minus 10 kilovolts per centimeter. And all the devices, they have a figure of merit. In this particular case, there are several factors. One is the quality factor for the resonance, that is Q factor. For the case of EEG, it is anywhere from 1000 to 5000. And the quality of the number that would define the performance of the resonator is the ratio of the tunability divided by the line width for the EEG, that ranges from 30 to 120. And you can make a similar resonator with a ferroelectric. These are ferroelectric resonators, and you can tune them with an electric field. And if you put together a resonator with BST, that is barium strontium titanate, the Q values range from 110 to 100, and this figure of merit is 7 to 14. So, this device is, it has much better numbers, both Q and F, compared to ferroelectric only resonator. And okay, so this is the same device. What is shown here is the tuning over a very small electric field range, which is rather linear. So, you want linear response for tuning if at all possible, but if you want to have it, then the electric field range is rather limited. And looking at it, this is non-linear, it is not quite linear, but you can make it linear by working at a very small interval for the electric field. That is what is shown in this case. So, as you go to higher electric fields, it becomes non-linear, and also there is hysteresis certainly, and it gets worse if you go to fields on the order of 20 kilovolts per centimeter. Right, this is PM and PT. The earlier one was with PCT. It's similar behavior, except that the Q value for resonance is around 1000, which is same as what we saw for PCT, and the tunability is 25 megahertz. So, it's not any better than what we got with PCT, but this is better in the sense that we are using here single crystal PM and PT, which is rather expensive compared to very cheap polycrystalline PCT. So, this case was where we used eutectic bonding to make the bilayer of EG and PCT. And so, the idea is to compare what happens when you use a bilayer which was formed with epoxy versus eutectic bonding, and we found that it is not any better than the epoxy bonding. So, why take all the pain to make the bilayer by eutectic bonding, and there is no reason to. And these are similar data for a sample of 1 micron thick nickel ferrite deposited on PM and PT or PC and PT by metallo-organic chemical vapor deposition. The deposition chamber is enclosed. There is a substrate of some material. It can be magnesium oxide or magnesium aluminate. Then you heat the substrate to about 600 degrees. Then you let the gas flow right on top of the substrate. So, the vapor has nickel in it, iron in it. So, it will deposit nickel ferrite at appropriate condition onto the substrate, and it is a very slow process. So, ultimately the thickness of the film is only 1 micron, and what is shown here is the FMR profile for the film as a function of the electric field applied to a bilayer of this film with PM and PT. So, you see that the shift that can be accomplished with the electric field is rather small, and the line width, the FMR line width, if you calculate the field separation between the peak and the dip here, that is more like 500 Oersted. And the tunability for this range of electric field is only 260. So, only 1/2 of the line width, just to demonstrate that this is not something you would like to use for any tunable device applications, and this is on PZ and PT, and the film on PM and PT, it was rather poor tunability compared to this, but PZ and PT has a much higher piezoelectric coefficient compared to PM and PT, but in spite of that, this tuning is no good as far as the device application is concerned. Now, this is zinc to white, it is white type hexagonal ferrite bonded to PM and PT, and this can work at much higher frequency as high as 24 gigahertz, and in this case we are able to achieve tuning by about 25 Oersted, and so it has the right characteristics for devices operating at a much higher frequency than what the frequency range one would use for EEG based devices. So, this is eclectic bonding zinc to Y, PM and PT. It shows the tuning of the ferromagnetic resonance under an electric field from 0 to 8 kilovolts per centimeter, and so the converse magnetoelectric coefficient for this system is 10 times higher than what we saw for EEG. It is close to 10 Oersted centimeter per kilovolt. So, these are two different cases, eclectic bonded and epoxy bonded. In this particular case, we found that the eclectic bonding was preferable compared to this one. So, when we go to higher frequencies, about like 50 gigahertz or more, what you would like to use is barium hexaferrite or strontium ferrite. The reason is that they have very high uniaxial anisotropy field. So, the external field that you have to apply for ferromagnetic resonance is not that high. If I want to use EEG at this frequency range, you have to apply a field of 20 or 25 kilohertz. That is rather high, whereas with this kind of uniaxial magnetocrystalline anisotropy, all you need is maybe 3 or 4 kilohertz. Okay. So, these are ferromagnetic resonance in a film of aluminum substituted barium hexaferrite. The aluminum substitution is very strange. Aluminum is non-magnetic. So, what happens is the uniaxial anisotropy field is the ratio of the anisotropic constant divided by the magnetization. When you substitute aluminum, both the anisotropic constant and the magnetization would decrease, but the catch here is that the magnetization decreases much faster than the anisotropic constant. So, you essentially you can increase the anisotropy field just by substituting aluminum, and that is what we found out. This the figure here at the bottom, it is it shows the anisotropy field as a function of aluminum substitution, and for 0 aluminum it is around 18 kilohertz, and with aluminum substitution you see a dramatic increase in the anisotropy field, and you can reach a value of around 34 kilohertz for aluminum substitution by 2. So, it would allow you to increase the device operating frequency just by substituting aluminum without having to apply higher and higher bias magnetic field. And in this case, what is shown here is the ferromagnetic resonance profile for a series of bias magnetic field. So, as you see here, the frequency where the FMR comes in, it increases from 47 all the way up to 59 when you increase the bias field from 4 to 8 kilohertz. So, these are the frequency versus magnetic field for series of aluminum substitution. As you see here, you can reach a frequency as high as 110 gigahertz with this aluminum substitution. So, there are devices operating at this frequency. They are used for satellite communication. So, the hexagonal ferrite based devices are very useful for this kind of frequency range. So, when you go to 50 gigahertz or more, we cannot use a strip line. Instead, we have to use a waveguide for the devices, and that is shown here. This is a waveguide chart, and the barium ferrite bonded to PZT, it forms the block here. So, the bilayer is placed at the open end of this chart, and then you excite this with microwave power from a vector network analyzer, and this is the FMR profile for the resonance in barium ferrite for a series of electric fields. It's rather small tunability, it's about 10 megahertz for a field of 10 kilovolt per centimeter, but it's extremely very high Q value for the resonance. It's close to 50,000. So, the figure of merit is still reasonably good. It's the figure of merit is 30. That's not so bad. Okay. This is the same device, and so this one is pure barium ferrite, and this case is with aluminum substitution, and the FMR is seen at 106 gigahertz, and the tunability is by 3 megahertz for 1 kilovolt per centimeter of electric field. Okay, this is what I call a band pass filter. In this device, based on YIG PCT, there are two microstrips. One is at the input, one at the output. The sample is placed in such a way that it lies across these two microstrips. So, what happens is when you excite this with microwave power, there will not be any power transmitted to the output until you reach ferromagnetic resonance in YIG. So, under that condition, the magnetic film will absorb microwave power, and it will ultimately transmit that power to the output. So, it is like a filter. It allows only a certain range of microwave power with particular frequency will pass through. So, it is a band pass filter, and that is shown here in this profile. The profile shows the transmitted power versus frequency for a constant bias magnetic field. So, you satisfy the ferromagnetic resonance condition at 6.65 gigahertz. Then you apply an electric field across PCT. It moves the whole entire pass band from 6.65 to 6.725. Then you increase the electric field further. So, the pass band is shifted to higher and higher frequency as the electric field is increased. So, that is tuning the operating frequency of this filter. Okay. So, you can tune it by as much as 125 megahertz for a field of around 2.5 kilovolt per centimeter. And the figure of merit for the band pass filter is the figure of merit for the resonator divided by the insertion loss. What is the insertion loss? Look at the number here. The power transmitted at resonance is around minus 4 dB. That means, if there are no losses, you have to have this P right at 0 dB, whereas it is not at 0, it is at minus 4. So, there are losses in all of these parts. There is a loss in the microstrip that carries the microwave power, and also there are losses in the yttrium and garnet. These are magnetic losses. There are losses in the ferroelectric. So, that combines together to give rise to an insertion loss of 4 dB in this particular case, and you want to keep it as small as possible. So, this is the same device. Right. So, you can put together a dual resonator filter where there are 3 microstrips, one at the input, then one there is an intermediate one, then there is an output. Then instead of only one EPCT, you have 2 of these elements. The idea is when you have a dual resonator filter, you can have a pass band which is rather flat but wide. So, if you want the filter to work over a wide frequency range, so you have to increase the number of resonators from 1, 2 and 3. So, that is what is shown in this particular case. And phase shifters, they are used in phased array radars. So, in phased array radars, like for example, if you want to scan the sky for any object, then you have to direct the beam in a particular direction, and you can scan the beam over a wide angle. So, the phased array radars have phase shifters that would allow the beam to be directed or scanned over a certain angle, and YIG PCT can be used for that kind of application. And but I don't want to spend too much time. We are running pretty close to my time limit. So, with YIG PCT, you can apply an electric field and change the phase, and then do the scanning with this kind of device. So, I can put together a similar phase shifter operating at much higher frequency from 10 to 24 gigahertz with a bilayer of zinc 2Y and PM and PT. And these are phase shifters operating at 50 gigahertz using barium hexaferrite. So, what is a delay line? When at the receiving end of a radar, you have microwaves coming in. So, you can have the resonator pick those frequency band, but ultimately you want to have the selectivity for a particular frequency. So, that is where the delay lines come in. So, as the waves come in and propagate through the YIG, so you can separate them in time domain using this delay line. So, it will convert the signal from the frequency domain into time domain, so that it will be received at certain time intervals, and that is what is shown here. The time delay over a certain frequency range. These are not ferromagnetic resonance, they are called magnetostatic surface waves. So, just take it for granted that they come in and you have the waves over a certain frequency range, and when you apply an electric field, the time it takes to propagate through the YIG film can be controlled. So, as you see here, you have the control with an electric field. Under 0 electric field, the time delay will be around 200 nanoseconds. When you apply an electric field of 8 kilovolts per centimeter, it comes down to 100 for this particular frequency. So, that is how these can be useful. And attenuator are used if the incoming power is too high and you do not want to expose the circuit elements to such a high power, because they can just literally burn them up. So, attenuators are used to decrease the incoming power in a device, and that can be done with YIG, PM and PT, and that will give you the ability to control the attenuation. These are based on ferromagnetic resonance in YIG, by applying an electric field, you can tune the ferromagnetic resonance, and that way you can tune the attenuation. If you are sitting at particular frequency, for example, 7.24, you see here the profiles, as you go parallel to this frequency along this axis, here the attenuation is minus 15, then it goes to minus 10, minus 3, and minus 1. So that's the way you can change the attenuation for the incoming microwave frequencies by changing the electric field. So the hybrid wave devices, they are based on that it's a combination of the dielectric resonance in the ferroelectric. In this particular case, it's a platelet of bismuth strontium barium strontium titanate. Then you have magnetic resonance in YAG. You combine the two resonances to make hybrid waves, and they are tuned with an electric field or a voltage. It's ranging from 0 to 800 volts. The tuning that's shown here is by close to 400 megahertz. Okay, so this is a hybrid wave device, but the only problem here is they are much higher in terms of losses compared to FMR based devices. So it's a phase shifter based on hybrid waves. All right, to summarize, I talked about dual tunable high frequency devices. If you want to change the operating frequency, and if you have the ability to apply a variable bias magnetic field with the use of either a solenoid or you can use a permanent magnet, then you should be able to tune the position of the magnet in and out with some kind of a mechanical tuning. If you can do that, then you can tune the frequency also. But with a permanent magnet, the field that you apply to the film is non-uniform. That can lead to a spread in the FMR profile. So instead of 1 Oersted for the YAG line width, you may get 10 Oersted because of the non-uniform magnetic field. But if you can live with it, then you don't need any PCT or you don't need any voltage source. All you have to do is tune the magnet mechanically and you should be able to get it. And so we also looked at voltage tuning of resonators, filters, both passband and stop band filters, phase shifters, delay lines, and attenuators. So the advantage here is with voltage tuning, it's passive. That means it requires very little power. PCT has a very high resistance, and when you apply voltage, there is very little current. So the overall power consumed by the tuning mechanism is extremely small, just few milliwatts or microwatt. So these can be miniaturized very easily, and also you can integrate them with any semiconductor device, and you can put together the whole circuit on a circuit board, whereas that's not possible if you go for magnetic field tuning. And they are quite useful. And also we are working on how you can enhance the tunability over several bands. That's something that may occur in the future, but at this time the tuning range is very small, and it can be useful if you want to compensate for any change in the temperature of the operating device of these signal processing components. Otherwise, you cannot imagine having the tuning from X band to K band to millimeter wave frequencies. That's not what we are talking about. So limited range, but very power efficient, and it's still useful for many applications. Okay. All right, thank you. Any questions? Yeah, that's very critical because when I talk about EEG-based devices, if you have power more than a few milliwatt, then there are called what are called spin wave instability. It can create a real problem for the device to operate, and you have what is called high power effects. It can lead to secondary absorptions and also excessive heating of EEG film, and it will stop operating. So, it is very, very important to make sure that the power under which these devices operate is not than or not more than few milliwatt. If you go up to 100 milliwatt of microwave power, everything falls apart. Yeah, that is a good point. Yeah, you are right.
Most of the devices, dimension plays a very important role. Assuming that you are using the ferromagnetic resonance, the waves that are generated within the material, if we control the dimension of the material, will there be any other improvement in that? Because there may be a standing wave formed within the material due to the spin waves.
Yeah, so most of these devices, the EEG film is very tiny, maybe like 1 millimeter wide and few millimeter in length, because in case if you are applying an in-plane field, you want to make sure that the demagnetizing factor is small. Okay. So, thin film, long and not so wide. But apart from that, if you have a very large dimension for the EEG film, then you tend to excite several standing wave modes. So, there are series of standing wave modes, and instead of one single FMR, you may end up with a fine structure spread over a certain frequency. So, the frequency selectivity may go bad if the film is very long. But what is the limit? That is something one has to be careful, but it is just by trial and error. We can make devices with different lengths for the EEG film and probably come up with the optimum dimensions for it. Right.
Good morning. So second lecture for today is on practical applications of layered magnetoelectric composite for energy harvesting and sensing. And I'm very happy and honored to welcome Professor V. Subramanian from IIT Madras. For this, he has kindly accepted to be the guest faculty of this GIAN course, and it is going to benefit us with his experience. Before he could take over, I will give a brief introduction of Professor Subramanian. He is a Master of Science from the American College, Madurai, and then he did his PhD from IIT Madras. After a brief stint as lecturer in BITS Pilani, he joined IIT Madras in 1998. Now he is serving as a professor. His research interests include relaxer ferroelectrics, dielectrics, multiferroics, magnetoelectric, magnetodielectric materials. He also works on photonic crystals and metamaterials. He is involved in scanning near-field microwave microscopy, microwave passive and illuminated imaging, electromagnetic interference shielding materials, magnetoimpedance studies at microwave frequencies, and also black body radiator for microwave application. That's a lot. So we are looking forward to have a lot from him. He has published over 150 papers in refereed journals. He has presented over 100 conference papers, and he is awarded with 2 patents. He has guided 18 doctoral students apart from several MTech projects. He has completed more than 20 sponsored projects and conducted 3 short-term courses for the benefit of college teachers. He is a senior IEEE member, life member of IAPT, and fellow of the Academy of Sciences, Chennai. So I welcome Professor Subramanian.
Hello.
Here is pointer.
Not working.
It's only for camera. For
Okay,
you
not
can
working.
use this one.
Okay, thanks a lot, Professor Smita. Good morning, all of you. So today, my title is something like Practical Applications of the Magnetoelectric Materials. All along, I think for the last 4 days, even today also, we were seeing the total, the nature of the magnetoelectric material meant for the practical applications, naturally. Okay, so what is that I have to do more? Okay, if you see that we have more than thousands of papers coming out of this magnetoelectric materials. Okay, telling that we have very good sensors, very good tuners, and other things. Making it in a practical way, it's not an easy job, even though we say that it is, we know the properties of that, the variations, etc. It is not easy to actually implement it in a device. As Professor also pointing it out, power considerations, okay, heating nature, and the dimensions, all these things will play a part. If you are buying a cell phone, and then you say that I want to use this magnetoelectric material as a tuner, first question the Nokia fellow or for this Google fellow will ask you how much small the device is. Forget about the performance, you will first ask that. Because you do not want to have a very large mobile phone, at the same time you also do not want to have a very small mobile phone. Earlier we used to have a small phone, nowadays we are having want to have 6 inches, right? You are not happy with the earlier Nokia 1100. Phone is supposed to be meant for phone, but then it got into several aspects of that. So technology, it is not only for the communication, but also for very other things. People, their expectations are going to be different. So that's the reason actual practical application will have a certain difficulty. So I will give you one what we are trying to do some kind of a demonstration, okay, to see how people have to perform them. We need a pakka industry to sit with you so that you will be able to prepare that. Okay. So, before going into that, let me tell what we are doing. Let me thank our students, okay, Dinesh, Atal, Deepa and Subhaprada. Dr. Shashank is actually from Virginia Tech, okay. He is also our collaborator here, so I thank them. I also thank all the collaborators, okay, who have contributed to our development of this magnetoelectric devices. So, our lab actually does on a variety of things, not only for magnetoelectric. We also, as Professor Smita was telling, our area is going to be basically with the microwave, but then we do many other things, okay, with the center on the microwave. So, whether it is for the electromagnetic shielding, whether it is for the imaging, we work on that. Okay. So, these are all the things which we work on this. Here we work on the near field microscopy, far field imaging, then we have the microwave Hall effects, then we have the dielectric resonator based filters, okay, then we have the magnetoelectric device characterization setup, etc. These are all where, apart from this, we also work on this acoustic metamaterials, mainly meant for absorbers. Okay. So, these are all the various things which we work on. Okay. So, now you know very well these first 3 slides what I am going to tell you is what you have been put in your mind for the last 5 days. Even today you have to add it up. Okay. So, what is the magnetoelectric material? So, why we are not using single phase, why we need a composite, okay, what all the advantage, even if you say that sometimes the material, even though a single phase material may not be working so good, but for practical application sometimes it may be very useful, whereas most of with the advent of the thin films, we are able to use this magnetoelectric thin film materials much more effectively layered materials than that of the single phase material. So, there are pros and cons for both. Okay. So, this magnetoelectric material will be having several applications like sensing, gyrators, magnetic field sensing, this is current sensing, then energy harvesting, then this is once again the magnetic field sensing, but for geomagnetic applications. Then this is going to be E field or H field hybrid tunable microwave thing, which we last lecture we saw extensively about this. Okay. So, we have this direct ME effect and the converse ME effect, which gives you different applications. This converse ME effect is mainly used for gyrator applications, whereas direct ME effect is mainly used for sensing and energy harvesting. Okay. So, this we are saying this important thing is about the miniaturization of devices. This, when you compare to that of the earlier view graph, where I have shown about this dielectric based resonator based filters, you see the length and other things. But when compared to this ME material will be having a very small dimension. So, it all depends on what type of tunable devices you will be having. But nowadays the manufacturers, they want semiconductor based tunable devices, etc. So, we have certain advantages and, as I mentioned, disadvantages. So, these devices can be tuned by the electric as well as the magnetic field, and due to the single phase materials having certain weak values into that, you will be able to get a kind of a layered materials. Okay. Okay. So, once again these equations, which once again you would have to memorize it. Okay. You would already got memorized for the last 4 days. You will be able to see that the coefficients will be having the dependence on your magnetic restriction or magnetostriction you can have, and that of your piezoelectric coefficients. Once you are having this particular 2 properties, you will be able to say that I have got a very good material which can be tunable in nature. Okay. So, let me skip this once again. So, this is the important point which you will be knowing this. This particulate composites are having this low coupling, and because these particles, but it is very easy to prepare, and then making contact is also going to be very easy for that. So, for the device point of view, this is going to be very helpful. But the problem is that it is going to have a large leakage current and it's going to have a large loss. Okay, so this is the reason we are shifting from that of the particulate composite to that of the layered composite. Layered composite will have high coupling, but this coupling, even though we say that it is going to be the magnet restriction is converted into the piezo or piezo to magneto, you need a medium to patch it up. That means epoxy plays a part or glue plays a part. Without glue, people are also trying to use this heating, okay, means sintering type, no, and then that is possible to do that. But then due to the interface problems, we are not able to expect the performance to be high. Okay. So, here the thing is advantage is that we can have the higher coupling compared to that of the particulate composite, and polling can be done independently. It means for the magnetic separate, anyhow, because these are all ferrite materials, you don't need to have a separate one, but the polling can be done as per your wish. Okay. And then these phases are going to be separate, and therefore the leakage currents is also going to be minimum. Okay. So, there are a lot of materials which are having this layered thing, okay, like the PZT, NFO, etc., which are giving very high value of the alpha, whereas when it comes to the particular composite, all will be in terms of the millivolt per centimeter highest. So, compared to that of this is going to give you higher. Once you are having the dimension to be larger, and then you are able to generate more voltages, you also will be having large charges that will be within that, and therefore the power delivering capacity also becomes larger. Okay. So, whenever you are having this material, you want to know how the material is going to be characterized, you need a proper setup. So, we have this direct ME as well as a converse ME setup, which is built in. Mostly there is no commercial things are available. Okay, we cannot believe the commercial thing. Therefore, we make our own setup and try to use it. So, whenever you are having this layered thing, you need to start with the bilayer configuration, where we have this piezo phase and the magneto phase, which is going to be bonded together using a regular epoxy. There are several variety of epoxies available in the market. So, which one you would like to choose, that actually hampers your operation. So, that is another important thing which you have to take care whenever you are going for the practical application. So, as usual, you will be able to say that this alpha is going to be given by the formula V divided by H into 2P. And now, here you see that what all the layers involved in that, V is what your measured one, okay, and H you apply, and Tp is the one which you can control. But then this ratio, the V by H, is actually controlled by the material property, okay, and Tp is the one which you can externally control. That means once you are being given the material, you do not have any other choice but to play with the Tp, or here the thickness of the material, to get the value of alpha to be more. But please remember that it is not the alpha which is very important. It is the actual output voltage which is what is important when it comes to the practical use. If you are going to publish a paper, yes, I have got alpha to be something like 5 volt per centimeter, that is fine, no problem. But as soon as you want to use it in a practical application, you have to see how much would be the absolute voltage what you are getting it, and from there whether you will be able to use it for your sensing or for energy harvesting applications. Okay. So, that has to be taken. So, whenever you are having this application in mind, I have given you, there are several other applications available. I have given you 3 different types. One is going to be the magnetic field sensing, another is going to be current sensing, and that of your energy harvesting. These 3 we can see that whether how people are utilizing that. Okay. So, whenever you are having this magnetic field sensing, people generally use this direct magnetoelectric nature, and then that can be used to detect both AC and DC. It all depends on how you configure this particular measurement procedure. You will be able to use it for direct your DC, direct current sensing, or the AC magnet, AC current, etc. Similarly, whether you are, because of this AC current, you will also be able to get the AC magnetic field and DC magnetic field. Okay. So, what is the use of this? You can use it to do variety of things like, finding objects buried under the earth, and then in quote unquote you can use it for mine detection. Okay. Then magnetic field mapping can be done, because this is another important aspect of that. Then when it comes to the current sensing has another application, like you cannot simply put a device to measure that, and therefore these things will be direct magnetoelectric material can be used to detect the DC current as well as the AC current. When it comes to the energy harvesting, people use mainly this direct magnetoelectric material, and this, when it comes to the energy harvesting, you do not worry about how much energy we are spending, because we consider this as a kind of a stray amount is being given, and then from there we are able to do it. But then just because stray magnetic field is being converted into the energy, one has to see how much is the efficiency. It's not that we should not bother about that, we should bother about how much is the conversion efficiency of that. That means you apply an external known value, how much power or how much energy you have spent on that, then see how much energy you are getting it back. So this is the important thing which many of the people forget. Okay, we are only worried about whether we are able to glow the LED or etc. Even I will also show glowing the LED, but then we forget that how much would be the exact power conversion efficiency. That is what is another important factor people have to remember. Okay, what are the variables playing in that? Okay, so even though assuming that I want to make a device, then I should see what all the variables I should have. Okay, how to improve? These two are very important things. Okay, so whenever you see this variable in this particular case, okay, one should know what is the nature of the application. So what is that device is going to do? If the device is going to make a sensing, then I should know its sensitivity, how much sensitivity should I have. Okay, so for sensitivity, what is it in our case? In our case, the potential difference is what I will be using it. But what is that I am sensing? I am sensing the magnetic field. So that is the base. So magnetic field sensing will give you the potential. So what is important is the measured quantity, the potential. Because here I know what is that input magnetic field. If my voltage is going to be larger or smaller, it gives me the freedom to exactly tell you how much I can go around. It means I will have a sensitivity and the limit of detection. These two are being controlled by that. Okay. So then for the energy harvesting, as I mentioned, power delivery is important rather than the value of alpha alone. Okay, we need how much power. That means we need not only the potential difference, but also the amount of charges flowing in. You may say amount of charges, it's nothing but the current flow in that. So that also is very important in that. So then the power dependency of the variables, I have to check. So that comes from the material property. So now you see that the material has to have a large piezo restriction, it should have a large magneto restriction, etc. To get a large value of alpha. Once again, when I tell you alpha, it should be tied up now with the absolute value of the voltage what I am measuring. Now, so and also not only that, I think professor has to gave you the important thing during the first talk itself about the ratio. So the dielectric permittivity and how much would be the external magnetic field getting converted into the material. That means B is very important rather than H. Okay, so the conversion is going to be given by this magnetic permeability. So these two are going to be very important for you to see whether I can utilize the material properly or not. Then comes the external influences. Even though you are having a very good material, then your external influence can spoil everything. Okay, so that is something like how much the proper bonding you are going to do, then where you are going to use. The temperature is very important. The operational temperature is going to be very important for them. And then not only that, you are going to use it for magnetic field sensing or for energy harvesting, you should know where the sources is. If you are going to make it for a sensor, okay, then the stray, what is that you are going to measure? Then apart from that, what else you are having? That means you are not only measuring the magnetic field from a motor, but then surrounding that there are several other magnetic field sources available. The known sources are immediately you will know about the Earth's magnetic field. But apart from that, you have several other sources coming into picture. Okay? Even your own other nearby vehicles and everything will also, or motors will also affect that. So one has to be careful with that. So when it comes to the case of the epoxy, you know that there are different types of epoxies available. Example going to be Devcon, M-bond, Sticast, etc. and silver based epoxies are also available. So these type of epoxies will actually affect your performance. So in order to know what type of epoxy I should be able to use, I should know very important factor is the material property. Here also epoxy has a material property. Most of the times this piezo or the magnetostriction, they will be able to work only in its your elastic limits. Your Young's modulus is going to be important for that. So this elastic limit is going to be governed by Hooke's law. Anyhow, we are not going to apply very high amount of magnetic field or very high amount of electric field. So naturally it comes within that. When it comes to this epoxy, epoxy is not sometimes, even though we know the rubber, I can stretch it. How much I can stretch? Certain limit of that. Now the thing is, the thickness of the rubber is very important. If I go to the shop, I can buy a thick rubber band, thin rubber band also. So that plays a very important role. How much can be stretched, etc. The Hooke's limit will get changed. So the nature of the epoxy is also plays a very important role. So here if you see that by simply varying this, the epoxy nature of that, the epoxy value if you are going to change it, the nature also changes. Therefore you see that the alpha value varies right from your 5 volt per centimeter oyster to that of your 50 volt per centimeter oyster. So one has to be very important. So if you see that the epoxy's Young's modulus, it becomes a very important factor in that. The Young's modulus is going to be smaller, naturally I get a smaller value. If Young's modulus is larger, I will get a larger value. That means I can put because Young's modulus is going to be given by nothing but the strength. So the epoxy has to be nicely extending. At the same time, its elastic limit also should not be reducing. So that is two are important into that. So that tells you how much magnetic field can be applied onto that. Okay. So now you have got variables you have to check for. You have got only one equation. What are the equation you are getting? Your V output, what you are getting it is going to be given by your KQD. So KQD nowadays you will remember that. Okay. Then by your HAC. Okay. This what is your alpha. Okay. KQD is your alpha. Okay. Then your T thickness of your piezo material. Then your HAC. That's because T is going to be. Now you see that for alpha value you want T to be very small. We are very happy with the large value of alpha. But when it comes to the measurement, I can't use a multimeter. I have to go for a nanovoltmeter, okay, because the TP is going to be in the numerator here. So one has to be careful with that. So what the thing you have to use. So optimization is very important in this aspect. Okay. Yes. Huh? Huh? Yeah. Previous. These three will give you, that is a coupling coefficient. These three will tell you about the alpha value.
That is electromagnetic.
Yes. Okay. So your QD is the one which your piezo magnetic coefficient. I don't need to even say this. Okay. So now the practical problem is that after making the device, I should now check for signal to noise ratio. How much noise I am getting in the system, and stability. So it is when I am using an amplifier, I should know the stability of the amplifier. It will drift with the time, the temperature, everything. Okay. Then vibrations, that is another important factor. So temperature is also going to be there. Okay. Vibration, other unwanted pickups will be there. So all these things will play a part when it is coming to the realization of a device. Okay. So how to, there are certain factors which you have to enhance that. How to enhance that? You know that selecting a very good material is very important. If you go through many papers, you will get several standard materials available. But then as a student, you want to first publish a paper. So what do? You just go for a new material, right? So for a device person, I should not worry about new or old, etc. I will have to look for standard. That is the reason most of the papers, where they want to apply it, they use metglass, terphenol. They are not at all worried about new magnetic material. Okay, they will only use the standard one and then try to improve and reduce the noise and then increase the sensitivity. Okay, so here you have to see about this piezo and magnetostrictive coupling coefficients or coupling nature of that. Okay, so you need to have a very high magnetostrictive and with high magnetic permeability. This is mainly because, as I mentioned, that you are giving externally H, but internally, in order to do everything, you are going to have a B. Okay, so that's the reason B becomes important in that. Okay, now it becomes the elastic property. So elastic property is going to be the Young's modulus. Okay, that has to be there. Another one, our professor always tells you about the losses, high resistive, etc. So one has to have a minimizing the losses. Okay, the loss nature has to be lower. Otherwise, you have a problem about converting to the voltage. Okay, because leakages are going to be larger. That has to be stopped in that. Now comes the geometric parameters. Now thing is, as I mentioned, thickness you can vary, but then what else it can have, because you are going to make a material, and whenever you are going to have a strain, when Young's modulus is going to come into picture, naturally you got a resonance. So the natural resonance of your material comes into picture. That material is not dependent on the material, that the resonance does not depend on the material, but it depends on the dimension of the material along with its property. So the dimension plays another important factor in that. So this, you have to have a proper thickness ratio, okay, and you have to proper dimensions. This thickness ratio comes mainly because between, whenever you are attacking two materials, there is always a strain developed in that. Okay, how this distribution of the strain is going to be there depends on what is the bottom and the top, the two players involved in that. So if you see that, depending on your MPM structure, I think this also, I think you have a video for that, I think so. So this MPM structure, if you see that in LT configuration, you know standard what is L and T, right? So L and T configuration if you are having, then you will say that theoretical paper suggests 0.67 approximately. Experiment also suggests that the thickness has to be of the order of 0.67. But please do not go blindly with that, because this particular value depends on material aspect of that. Not all the materials will be having 0.67, etc. If you are having this particular configuration, once again, people do not bother about this configuration. They simply take it from the paper, apply it on that. That you please avoid. Instead, you try to make your own material and then try to vary the thickness and find out what should be the optimum thickness variation. You may take another 2 more months, doesn't matter. You will be able to get for your material what should be the thickness ratio has to be there. Once you are getting this thickness ratio, you will be able to get a good geometric parameter for your device. Then comes the layer dimension. This layer dimension is mainly for your vibration. So you have the radial mode, okay, then your bending mode, and whether it is going to be symmetric device or asymmetric device, all these things will come into picture when it comes to the your bending mode. Not only that, is it going to be rectangular or is it going to be circular, means it's like a pellet, or is it going to be like a plate, etc. That too depends on, that tells you about the dimensions of that. Once again, if you are going to use it for a device, the frequency of the device is becoming important. So which frequency for which you are going to use, so that you select it, depending on that you make it. Therefore, sometimes I may not be able to get the proper dimension, but sometimes my frequency may have been different. That time what I should do, I should load the device. So I have to use certain kind of a loading. I can clamp it. Once again, the nature of the clamping is very important. One side clamping and both sides clamping, or center clamping, or all these things play a part in changing the frequency of the resonance. Okay. So this is one such example where people have changed the length of the material. Okay. So from 12 to 18, then you can see that it starts increasing. But once again I say 18 is not maximum, because whenever somebody says that 18 is maximum here, so I will stop with 18. That is not the case. You have to go to 20 and check whether increasing or not. Okay, that is another important case. So depending on what frequency you want, I want a frequency of say 100, then I may get here, so I may change to 17 mm. Then is it sufficient enough? That I have to verify. Sometimes I may have to use a different material values and then to load it or add something certain extra weight, so that I will be able to tune that. Okay. So it depends on what frequency you are having. Going to very high frequency for certain purposes is useful, but whereas most of the practical applications where you want energy harvesting from the motor, from the farm motor or from the bike, all these things you have to select the frequency and then choose your device according to that. Okay, so this was the same thing. So when it comes to the radial mode as well as the bending mode, then you will be able to see the geometric nature of that and then try to use this formula where the resonance for frequency for the radial mode is given by beta by 2 pi r square root of y by rho into 1 minus v square. Okay. And this, if you do that, the variation is going to be the radius here, whereas in the case of the bending mode, here it is going to depends on your once again radius and the mostly radius here. Okay. And the non-uniform nature is very important. Okay. So here it becomes the asymmetric nature is what is important for the bending mode. So if that's a symmetric thing, then the bending mode is going to be very, very less. Okay. So the contribution means it will not even appear into that. Whereas for the non-uniform, yes, it is going to be appearing on that. So it is easy to do that. Okay. So one has to see it's before making or once you make the device, you just go through the impedance spectroscopy for that. So here the impedance spectroscopy becomes very important factor. So you see the impedance spectroscopy and identify the resonance modes into that and then try to play with that. Okay. So if you are able to change the material properties, fine. Otherwise you have to change the compositions and other things to do the modifications in that. Once again, factors to enhance, you are coming back to that. So it comes to the interface quality. As I mentioned that the Young's model of the epoxy is going to be important. Then that also goes to decrease your defects. Defects also in the interface has to be lesser. Whenever I say that whenever you are going to not to use the epoxy, but then you are going to use this directly heating it, no, that is sintering, okay, and or annealing, okay, with both the things without bonding, you are going to do that. The interface effects will be having large play in that. It will have a lot of defects. So to avoid the defect, you have to take care of that. Okay, there should not be any voids within that. So you have, whenever you are going to do that sintering, etc., one has to be careful with that. Then, as I mentioned that you can do the frequency tuning by adding the mass, okay, or pre-stressed conditions in that to change the natural resonance frequency. So this is the same thing I am repeating it here. Okay. Okay. Then will I stop? Can I start doing that? Don't do it. Okay. Now go for a simulation. Okay, because this is another important factor. One student has to do that. So if you are going to do the simulation, that will help you a lot of time. Okay, it will save lot of energy, time, etc. So what are the earlier, say 15 years back, we never had a proper multiphysics simulation technology for that. So we were using something like FEMLab. Okay, FEMLab had a very limited capability, or all other finite element methodology labs will have very limited capabilities. But nowadays, more and more people from physics, they join the software and try to use this material measurement. Okay, so material capabilities, they are incorporating. One such thing, people use this as a COMSOL, which is going to be nothing but the old FEMLab. This COMSOL has a lot of multiphysics things are there. It is not that only COMSOL, there are several other multiphysics softwares available for that, which you can utilize it to see about what will happen in that. This gives you two things. One is you don't need to do actual measurement. Okay, you can actually simulate it and find it out from the given properties. Okay, and then find out what should be the bending mode, where should be a radial mode and other things, and see that. Not only that, you can actually put epoxy properties and check how much would be the variation. So what is that you do? You choose the appropriate interface for the simulation study, whether it is going to be Magnetoelectric. So you have to have two physics problems. One is Magnetoelectric problem, another is piezoelectric problem, third one is interface problems. So, these three problems have to be put together in that. Okay, here the thing is all the material properties have to be put in proper. Once again, any mistake or any variations in the material property will also affect yours. So, it is not that this gives you only the kind of a indication to that. So, then you go actually do the measurement and then come back and then manipulate the properties, vary the properties and check where could have been the variations in that. So, you do this magnetosection piezoelectricity along with the epoxy nature of that and then do the physics interface. Then you go for the material properties and do the boundary conditions properly. So, the boundary condition becomes clamping becomes important. So, the edges, so that is free to move or any conditions you are having. Once you get to the boundary conditions, you generate the proper mesh and then try to do the simulation. Once you do the simulations, you run the setups and then now compare the experimental data. That is very important. So, you have to compare the experimental data and then try to match that. So, take a known thing, do the whole thing and verify, then go for a variations in that. So, that this will be giving you a lot of time, okay, it will save you a lot of time to do the actual thing, okay, because the cost of the material is going to be so high, you can't waste the materials into that, okay. So, these are all the things which we have done it for nickel ferrite and then BCT, PCT, how one can actually use it in the simulation conditions and then try to do that. So, this also gives you more the information about the bending mode, radial mode and other things, and then you will be able to tune it, etc. So, it gives a kind of a visual or quote unquote nice play. It gives you like a video it gives, and then you will be able to understand the nature of that. Okay. So, now we go for the sensing. Now, magnetic field sensing, when you are going to have that, it's already to 11:45. Okay. Okay, magnetic field sensing, when you are having that, okay, then the important nature is that without magnetic field, our life is going to be hell. Okay, we can't have. The thing is, all our navigation systems, okay, they require that. Okay, and on Earth, it's a very good, it's a big magnet for that. Okay, and due to the ion, molten ion, which is rotating. Okay. So, we get the magnetic field, and then as usual magnetic field north is nowhere related with the physical south, okay, it's slightly deviating from that. And all the migratory birds, they utilize two things, one is visual communication and that of the magnetic field lines. With that only they are migrating. And what for we are going to use it? We are going to use it for finding submarines, okay. And then we are going to detect, as I mentioned, the mines, okay, and any other buried objects, and any land, any variations happening in the beneath the crust, you will be able to evaluate that. You can even find it out. Okay. So, for all these things, we will be able to use it. So, what is the easiest way to do the magnetic field sensing? Take a simple wire, make a loop, and then you can measure the current flow. That then depends on the limit of detection, depends on how much should be the current flow and other things, okay, how much you would be able to measure. So, the whole limit of detection sensitivity depends on which instrument you use it for detection purposes. Okay. So, we have the Hall effect sensors, okay, which will be giving you a very nice DC, and also AC Hall effect sensor are also available to measure the AC magnetic field. So, as I mentioned that for the high health and other high power industries, magnetic field sensing becomes important. So, MRI is also mainly because of that. So, all these things will tell you about the importance of your magnetic field sensing. Okay. So, whenever you are taking this Earth's magnetic field varies at each and every location, not only varies with the location, but also with the time it is varying. That is also another important factor in that. And this time variation depends on two things. One is the Earth nature, another is the external one. So, all the sunspots and other things, even moon, okay, they all will be affecting our Earth's magnetic field. So, the nature of the variation tells you that. So, India has several locations where they measure the Earth's magnetic field, and in Tamil Nadu we have in Tirunelveli here, and then for Mumbai, that is where the headquarters is there, so in Maharashtra. So, they also do the Earth's magnetic field measurement and then collaborate with that, with the other people. Okay. So, as I this is the variation, if you see that, and the field varies between 40 to 60 microtesla, okay, for the Earth's magnetic field, okay. And as I mentioned that it is magnetic meridian, nowhere it matches with that of the your geographic meridian, etc. And it's mainly useful for guidance and for positional location, and also can give the anomalies indicating out of the huge objects. When I say huge objects, the submarine variation. Otherwise, to detect a submarine, we have to use a sonar, which is once again, they detect from where the source is coming. So that becomes a counterproductive. So that will be a problem. So we have to use a kind of a magnetic field variation to do that. Now nowadays they are using drones fixed with the magnetometers to check it up whether there is a variation there or not. And people are also using satellites to know about the location of your submarine without sending any other signal to that. Okay, so simply they measure the magnetic field variations from that. Okay. So this is the one unit which they use to get to the magnetic field variations, okay, in a globe, okay. This is not an actual thing, so it's they made a globe and put a magnet inside and then use this magnetoelectric material, okay, and then this layered device to check it up. So here this whenever you are having this, they use this piezo fibers, so med glass PZD fiber they have used, and to know how much would be the variation. So whenever you are having this magnetic field sensing, as I mentioned, the voltage what you measure is going to be important. So it is not alpha which is very important. We are going to measure VME here. Okay, VME what we are measuring is what is important in that. Okay, so naturally this is given by the alpha and also that the your material properties. Okay, so you get the variation here. It goes up. Okay, for the two when it is having this 2L configuration, you are having this variation, that is for the noise variation, you do that. Okay. Then for the other variation, how the alpha value will be there, you can use that particular value to use as a device here. Okay. So they have used a toy globe, put a magnet, and then they have started measuring it. Okay. So this is what they do that. So another magnetic field sensing is that using the push-pull arrangement. When you are using this push-pull arrangement, you will be able to use the standard terphenol and that of the PMNPT. Here you see that because you are going for a device, you are not worried about polycrystalline or something like that, they go for a single crystal. But then cost is very important. Okay. So not to have a cost reduction, one has to go for a polycrystalline and then go for high centering nature, okay, to get a large grain growth. From there you will be able to evaluate that. So whenever you are having this terphenol, you get the longitudinal magnetization which giving you 900 ppm per 1500 oyster. So and use it for push-pull variation to get this. So they have used such a configuration to detect the limit of detection. If we say that it is going to be of the order of nanotesla. So they are able to get the nanotesla level of arrangement. Okay. So, so now under resonance when you are going to do that, this can go much higher. So whenever you are going up to the resonance, okay, you will be able to say, in case I am getting this 60 nanovolt as my detection level, then I can go up to 1.2 picotesla, but then it's something like 5 volt per oyster accuracy I will be having that. Here I am not worried about the power, okay, I am worried only about the voltage. Okay. So if I am able to have the capability to measure up to 1 microvolt, I can easily go up to 0.1 nanotesla with this particular arrangement. So as I mentioned that our Earth's magnetic field will be having of the order of 40 to 60 microtesla. Okay, so one will be able to check it up by making the device and then rotate it and verify that. Okay. So another thing is that if you are going to use these particular devices for low magnetic field, there is a small mistake here. Okay, this must not be micro here, it must be simply HAC. For a low magnetic field region, okay, you will not be able to see any changes in that. This is actually coupled with that of the strain nature. Okay, if you start from the 0 and then start increasing, strain will not be appearing till for certain H. Okay, then bias, then it starts increasing that. So this is the main reason where you will not be having. Another one is that the noise nature is going to be very high here. Okay, if you are neglecting this, then if you are going in this particular region, the noise is going to be very large. Therefore, signal to noise ratio becomes very low. So, here also it is not advisable to operate. So, even though you are having this, you are advised to operate only in this particular region here. So, one should choose a proper region to operate the device on that. Okay. Maybe for other purpose it may be very low here, for publication purpose it may be doing it, but actually for the device you have to fabricate, you need to have a proper linearity and other things. Okay. That to sense the current, okay, you will be using this flux gate methodology. This is a regular flux gate methodology people use, because if you are going to use the regular meter, you are going to put it along with the line itself. To avoid that, they start using this flux gate sensors. So, whenever you are going to use this flux gate sensor, the problem is that whenever you are you need to have the excitation coil as well as the pickup coil both together. So, when you have that, you will be able to evaluate it. But in the case of the magnetoelectric material, your magnetic electric material will be here. You have the pickup coil, your excitation coil, which actually gives you the strain, and what your generated output will be able to measure. But then the problem here is that the excitation what you are giving will also get induced into that. So, this also, but both the measurement frequencies are going to be the same. So, you have to avoid that properly. So, you have to make a larger device, and then the coupling has to be in one end, the other measurement device be made in the other side of that. Okay. So, this flux gate methodology will be able to use it to measure a very low value of the current. Okay. They have achieved up to even say like very lower than that of the in terms of the magnetic field is going to be micro Tesla, but in terms of the current it is going to be much lower than that. Okay. It will be nanoampere and or even lower than that of that. Okay. Okay. So, another sense of current, where low value of the current to be done is by using the different combination. Once again, the materials are not new. Please hear all these things. If you see that materials are not new, but the way you are using as a combination, okay, is going to be important. So, it changes. So, you are here, you are using the different combination. If you are using different combination with the standard material, you will be able to utilize it. Once again, what type of applications you are doing, what all the limitations you are having, all these things will govern to choose the particular configuration in that. For technologically, whether you will be able to make like this, okay, that is another important factor which you have to check it up. Okay. So, this here if you see that you are able to get the values you will be able to get it, but they use a small kind of a transformer here to avoid the impedance problems. Okay. So, this can be used to avoid the impedance, so that you will be able to use it effectively for that. Okay. Next comes to the noise in the system. So, whenever you are having this very low value of the magnetic field or in that, the noise is very important in that. Noise, if you see that there are two things when it comes into picture. One is due to the dielectric nature, another due to the resistive nature of that. Okay. So, you are having this C tan delta is nothing but your epsilon double prime, okay, means a dielectric loss of that. So, this is given by the factor of 4 kT epsilon double prime divided by omega, and then for noise due to the resistance is going to be 1 by omega square root of 4 kT by R. So, the total noise if you see that it is nothing but square root of ND square plus NR square. So, this noise is going to be a very important factor for you. So, whenever you are doing any measurement, okay, these are all going to be the noise involved in that. So, one should know about the noise. So, in order to do that, you always use a dynamic signal analyzer to get the noise. If you do not have a dynamic signal analyzer, then what you do is you measure as a function of time, etc., and see the signal noise in that, and then actual signal you means measurement you make it, how much would be by applying the magnetic field, known magnetic field, you know how much would be the voltage you are getting it. So, VME you will know what it is, and then if you do not have VME, you know what is the base noise you are going to have. That value you will note it down, but that time you will not get V per root hertz, because that is whether you are giving you the AC field if you are giving, then you will be able to do that. So, that is done by the dynamic signal analyzer, but if you do not have that, then you will be able to get only the delta V of that, which is due to the noise nature of that. So, once you are having this then you will be able to know the sensitivity of that. Sensitivity is always defined by delta V by delta H, okay, because that is what they measured quantity. So, delta V, how much you are able to do it. This delta V at the maximum or the minimum, I can say that has to be under noise. Okay, it should be more than that. Okay, so that's what is the one higher than that of the noise. What are the maximum noise you are having? That is what is given by the delta V, etc. Mostly it is given by the ratio, okay, that means slope of that you will be able to get it. The slope is very nice, fine. The slope is not so good, then you have to take properly this delta V by delta H. Then comes the limit of detection. Limit of detection, there are two things. If you are going to measure the magnetic field, then you go for limit of detection for the magnetic field. Okay, otherwise limit of detection tells you about this once again delta V will tell you about the limit of detection of that. So here limit of detection is given by this delta H by delta V in terms of magnetic into the signal to noise ratio into the noise voltage what you are having. This is going to give you the minimum amount of the magnetic field that you can measure. So that is also important in that. Okay. So now how to reduce the noise in that system? The noise is due to the temperature, vibration, external source of the magnetic field. This you can avoid it by using the shielding, okay, but that also affects our other applications. Okay. The vibration and temperature, they are affected by the configuration of this. So depending on whether it is going to be symmetric configuration or asymmetric configuration, these are all going to play a part. Whenever you are having this asymmetric configuration, you cannot avoid this vibration as well as the temperature, noise, etc. But one can do by taking two asymmetric things and then use a Wheatstone's type of bridge to compensate that. That is possible in that. Okay. So that also can be compensated into that. When you do that, or one particular example is that people have used this symmetric configuration with M-P-P-M configuration. Okay. This is a kind of a bimorph. Okay. This is called symmetric bimorph configuration. There are several other things also kept here. The symmetric bimorph configuration, one has to be careful in biasing that. So this is actually giving you the bias, so that you are changing the magnetization direction, okay, opposite to each other, so that you will be able to compensate the temperature as well as the vibration. So temperature compensation you see with that bimorph you are able to get it, whereas in other region you are not able to compensate that. So this people generally get this particular variation, that with the temperature, with the time it goes on increasing or decreasing. Okay, this potential can change, etc. So that can be avoided by taking two such setups and then compensating that. In case you are not able to do the symmetric, take asymmetric, but then make two identical devices and then compensate that. That is what is a problem. I think people can do that. Okay. So as I mentioned that the symmetric vibrations, symmetric structure and asymmetric structure, how it is going to be affecting that. Okay. So what we do is we actually made a small setup. It is not for the proper setup. It's a small setup we wanted to make it and see how it can be used. So to do that, we need to give we wound our own coil for the DC electromagnet. Then for the AC, we wound our own coil in that. And then we used a lock-in amplifier, a small USB based lock-in amplifier, which is very cheap available. Okay. Then we had this for power amplifier for the AC current, we used LM615T to do that. Once you are having that, we used a laptop to as a data acquisition system. And from there, we wanted to evaluate what actually, even though we have this BCT is a nickel ferrite, as the D33 of 380 picocoulomb per Newton, and this is going to be approximately 30 ppm. Okay, we are able to get a voltage of something like 110 volt. Now you see that the nature, its noise level is going to be very, very low here. Okay, so then we will know what is the variation of alpha here, and this thickness of this very important, is around 0.8 mm for the piezo. Here, please remember that this is not having that 0.67 variation. Okay, the dimension is of order of 2 into 1 centimeter square. So once you are having that, okay, you will be, this is our setup. You have here actually that earlier one was used to know the sensitivity. Now once you know sensitivity, you remove the HAC, okay, that you remove DC which outer coil you remove, only small coil is kept inside, and then sample is kept inside, and then it can be put on a trolley. You can put underneath, you can put any magnet source or anything to be detected, etc. can be kept on that. So we use it for two things. One is to measure, first of all, to know the Earth's magnetic field, whether it is doing it or not. The effect, that is also very important, because in the field trial you cannot say that no, I will be turning around, etc. So one has to be careful with that. And then we also use it to detect the current which is not passing through that. What is the easiest way is just to wind the coil on the magnetoelectric material itself, but here we didn't do that. Instead we kept the wire somewhere outside, it's around 5 centimeter from the sample, so that we wanted to measure a very weak thing. So the 5 ampere, even though we give that, we will be able to get only 0.2 arrested near to the sample. That too, it is going to be non-uniform nature. Okay, so from that, no, we will be able to measure whether how much would be the voltage, etc. For this, we give the DC bias, that is what is given by this yellow color coil, etc. So with this Hertz magnetic field, okay, we will be able to see we can measure the Hertz magnetic field with that, which is going to be giving you of the order of 40 microtesla, which matches with that of the location in Chennai. Okay. Okay, now comes the energy harvesting part. Okay, so the energy harvesting part, as I mentioned that there are, even though there are several varieties available, we use this magnetic energy, okay, which is going to be waste available in a waste thing. Okay, the application is that you can use it for many purposes. Okay, as a self-powered, most of the times self-powered devices. Okay. So I'll, because of time lag, I'll just skip this. It's only general information about what type of sensing you need it, etc. Okay. So there are several arrangements available. Once again, using the standard material, okay, you will be able to use different configuration and get large amount of power. So it's a very the two Hallback arrangements or Hallback configuration is very famous for that. So you put two Hallback arrangements and then run a rotating thing and then measure that. So put our material, okay, ME material, and then try to get the data out of it, means the power out of it. They could get the power, okay, with the load resistance, it will naturally vary at a frequency of something like 14.2 hertz. Okay, they are able to get a kind of something like 0.5 approximately milliwatt of that. Okay, here they have not told about the density, power density, but it's an absolute power we are getting it. Okay. Another methodology is by using this axial type. Okay, so put the axial type and try to measure that. Okay, you will be able to get the voltage of variation. No, if you see that they have to use it for the rhombohedral to orthorhombic transition alone. You have to use that. Therefore, what they do is from the terphenol PN, PM, and PT configuration, they applied a strain and or stress, external stress they applied, and then change the transition. Once you are having the applied stress, you will be able to see the changes to be more. Otherwise, it is very small, then the change is going to be larger. By doing that, they are able to measure this energy harvesting. Now, the thing is that is done by way of applying the pressure on that. Okay, so that's how they get that. Okay. Now, thing is another device what they have done is using this. This is one of the practical application they have found out, and they are actually using it in a microcontroller. And then using a Bluetooth transmitter, they are able to connect it to the smartphone. So this I have seen this kind of a very practical application they have done that. Okay, so here they have used nickel ferrite nanoparticles dispersed in PVDF TRFE. Yeah, so, okay, thanks. So, here it is, so the voltage what we may be getting, voltage may be here, but one has to get to the, use it for a practical application. So, what you should do is you should connect it to a rectifier, otherwise you will not get a DC power. Okay. So, connect it to the rectifier and then put it in a capacitor and then start using that. Okay. So, this is what is the charging when you are going to charge, even though you are getting a very low voltage here, when you are charging it you will be able to get the power as well as the proper voltage out of it. Okay. Okay, so another is dual phase. Here it becomes vibrational plus magnetostriction, both together. When you do that, you will be able to harvest more amount of energy. It is something like a hybrid type of things people are doing that. Okay. So, once again nickel plus a piece of fiber they are using it. Okay, here then when you do that, it's PVDF fiber only. Okay, so when you do that, you will be able to get at the different resonances how one can get that. Here you see that one side clamped. Okay, how the frequencies are going to be. So, depending on the frequency nature, you will be able to get a higher power output. Okay, this also I will just simply skip it and then we see what we have done. Okay, so here in order to do the kind of energy harvesting, we have selected this P and PT with the NFO. So, with that one is with the NFO, another with the nickel zinc ferrite. Okay. So, both we have used it to get the value of alpha. Once you are getting this standard characterization about the frequency, okay, resonant frequencies and other things, and then we will be starting using it for practical applications. So, here also another example is going to be BSPT nickel ferrite. Okay. So, once you are having that, you will be able to see the kind of a radial mode. So, you do the COMSOL simulation, identify the radial mode and then prepare the device and then check it up, how much will be the values, etc., whether it is matching and other things. Once you have done that, you will be able to do the actual measurement. So, by varying the thickness, okay, one will be able to see that this alpha value is going to be different. Okay, for 0.4 it is going to be less than 20, now it is going to be 0.6 mm, it is going to be once again less than 10, but whereas for 0.8 it becomes more than 25, mainly because you are able to match the radial modes of the and as well as the bending mode of that. Once you are going to match that, you are going to have a large value of that. But is it that always possible? Just because you are merging this radial mode and bending mode together, will you be able to get a higher value of alpha? It is not always correct in that, because the phase becomes very important. The phase becomes different, you will be able to get a different result. Okay. So, here luckily the phase is going to be matching. So, you are getting this alpha value to be of the order of 22.5 volt. I think this is 22.5 volt per centimeter rheostat. Okay. Another example is that in case it is not going to be properly matched, the phase is not going to be matched, you get a reduction in that. So, here in this particular BSPT NFO, if you see that actually we matched the radial mode and then bending mode, but we did not get a higher value, mainly because this phase of that, both the phases are going to be exactly opposite. So, for that what you should do is you should change the thickness of that properly and then get the things out of it. Okay. But that time we did not have the time, so we only found out. Okay. So, we stopped with that. Okay. So, once you are having that, you should be able to do it for a device in that. As I mentioned, this co-fired or the sintering, what happens in that, the temperature becomes very important factor. So, with the temperature, one has to see whether the performance degrades or not, because most of the practical application is not only at room temperature we do, we go temperature even up to around 50 degrees, etc. Okay. So, what you do is if you are having this epoxy added, you will be able to see the kind of a variation like this. Okay. With your temperature, the alpha value goes on decreasing like this. Okay. So, more than that of 50, you will start decreasing it very drastically here. Whereas, whenever you are doing this co-firing methodology, you will be able to avoid this particular temperature effects on that. But whereas you will be able to get some kind of a defects nature, if you are able to optimize that, you will be able to get a good result out of it. So, you are getting the 60, even though it is going to be smaller, it is a smaller value, 60 millivolt per centimeter rheostat. You see that with the temperature, it is not getting affected even up to around 180 centigrade. So, one can use it for practical applications nicely even up to around 80 degree centigrade, etc. Okay. So, once again, preparation methodologies also play a part in the alpha value of DME. Okay, so with the sintering conditions, how it is going to be varying from 1200 as well as 1000 degrees, because mainly because there are two different materials you are going to co-fire it. Whenever you are doing that, one has to be very careful with the sintering temperature. Okay, so we want to do the demonstration. What we should do is we should take it and then apply it to the rectifier and then put a capacitor over that. So with this, we have used this BSPT only. This is BSPT sample. When you do that, you are able to get a power something of the order of 1.2 milliwatt per centimeter square. Here thickness has to be taken into consideration. Here the resistance is approximately 10 kilo ohms. This is mainly because depending on the material what you are using, this output impedance is going to be varying. So you have to match the output impedance with that. So that's another job you have to do. So once you have a proper impedance, then you will be able to deliver the maximum current. So you have used around 8 LEDs to light up. Okay. So as I mentioned, that it is not only the voltage, means lighting the LED, but also power was what is important. So we do the power measurement also. The power measurement gives you the around 1.2 milliwatt per centimeter square. Okay. Then this is for a waste magnetic field. We want to do that. You put your sample in just outside the fan. Okay. Then you will be able to see the nature of the output voltage what you are getting. Here we have not measured the power, but you have measured the voltage peak to peak. Okay. So I can't comment on the nature of the power what we got it. Okay. Here it becomes the waste power only. It means waste energy only we are going to convert to that. Okay. So here this is for the PVDF TRFE with the nickel, and this is with the 48% nickel ferrite alloy, nickel ion alloy we are having. So this alloy is going to give you large value, mainly because it is having a very high value of the mu. For the same magnetic field, because of the large value of mu, you are able to get a large value of the voltage. So the same thing, it is being repeated here. Because of the 19,000 mu, you are able to see the kind of large value what you are having that. Okay. Now, whenever you are having this BCT sample, okay, which you prepare it and then make these studies on that. Okay. You will be able to see that alpha value is going to be something like around 70 millivolt, even though now here you are getting something like 70 millivolt per centimeter IR. This is for the with the nickel ferrite, you are going to add it up with the BCT, BST. Okay. So you get strain measurements, which is going to be giving you something like around ppm to be 30 ppm for the nickel, and then this for d lambda by dh we are going to do that. This is standard one, something like around 0.3, okay, ppm per IR you are getting that. So with this, you are going to add this BCT and nickel ferrite together. Oh yes, you have to stop that. Okay. So here you see that we are using this first bending mode for energy conversion, and then not this third one, which is going to give you a very large value of alpha. Okay, but we are using this first one mainly because for practical considerations, okay, we can't have 100 kilohertz. So for most of the practical, we were going to a lower value. So we used 11 kilohertz around that, which we applied 11. Means that's what the 11 kilohertz AC is needed. Okay, so once you are having that, you will be able to use this energy harvesting for that. So we applied once again this rectifier and then applying it. So what you get here is going to be a large value of 6.94 milliwatt per centimeter cube. So here the material is going to be new. Okay, this is barium calcium titanate, BCTZ with your nickel Fe. This is actually 48%. So this is something nickel alloy, actually nickel ion alloy we are using it. So which gives you a large value of your power conversion. So what is important is going to be selecting the material, okay, and then applying a proper configuration, and then what type of frequency you want, etc. What you have to decide, and then make a device out of it, so which you can use it practically, so that you will be able to know not only for demonstration but also you can use it for practical purposes. Okay. So with this, I would like to give a summary. What is that we have done? With the magnetoelectric layered material, one will be able to use it for sensing, energy harvesting, etc. But then it is not simply the value of alpha which is very important. What is depending on your nature of the application, you select. Okay, you get either voltage or the power. That is what should be the goal. But depending on whether you are an industry person or academic person, you can choose the nature of configuration and then perform that. Okay. Okay. So always assuming that you are going to operate in the field, which is going to be of around 80 degrees centigrade or more than that. And then if you see that not only the ferroelectric material, okay, you can also use the relaxer ferroelectric materials, which can have a large value of your dielectric constant, and also for the large number of temperature variation, it is not going to get affected much. So that is also another promising material people can utilize and then do the kind of a device. Okay. Once again, I thank Smita and Professor Gopalan for giving me an opportunity to discuss about this practical application of the ME layered materials. Thank you. Any questions? Any questions from you?
Is it possible to use particulate sample for energy harvesting?
No, particulate you can. It is not advisable to do that. Because particulate will have a, it will not be able to generate. But only thing is that in case you are not able to, certain locations, certain regions where you cannot use a layered, then there is a possibility. Otherwise, it's advisable not to use for practical applications. Okay. Yes.
So can this type of energy be stored? I mean, what I'm trying to say is, as the solar energy, we store it and then utilize when required. So you have used this energy for charging various things, right? So each time access to this energy may not be possible. So is it possible to store anywhere and then utilize it later?
Yes, yes. You can store. Once you have a capacitor bank,
Yeah.
you can store that. Okay. If you do not have any further questions, I'd like to thank you all for allowing me to interact with you further.